Alright, so lesson 7. This is still talking about the inverse of a relation. It's just part 2. I'll let you read through this review part at the beginning of the lesson. Now, talking here down here about the inverse of a relation. Okay, it's saying here that some relations are are functions and some are not. The inverse of a relation, which is not a function, can also be determined by the above methods. So the inverse of a parabola we know is not a function, but we can still figure out the inverse equation by switching the x and the y's. This particular one is a circle, center at 3, 0 and radius 3. Typically when you have the equation of a circle, it takes this format here. So when it takes this format here, we can read the center of the circle from that format and also the size of the radius. The number that it equals at the end here, r squared. So here we have 9. This is really r squared, the radius squared. So the radius is 3. That's why they're saying radius is 3. But we can also find the center of the circle. The center has coordinates h, k. So, for example, in this equation, reading h, you can see that h is actually 3, even though this says negative 3, because we have x minus h, just like x minus 3. So the 3 is the h. In other words, you can just take this value, negative value, and change the sign. Now, with the y, this is really, when you think about it, if we put it in this format, it's y minus 0 squared. So k here, for example, is 0. And so the coordinates of the center are 3, 0 with radius 3. It says here, describe how to use the graph of the relation to draw the graph of the inverse relation. So the graph of the relation has a center at 3, 0 right here. And if it has radius 3, it will go as high as this, as low as this, and it will go out to the side here. And over here, we can sketch this. But if we want to also sketch the inverse, then we can use the line y equals x coming down through here. Okay, so I'll just sketch that. The circle will look like this. And the inverse, we can take certain points, such as this one and this one. In fact, all of the points here, all 5 points that we have, and reflect them across this line. So this point is on the line, it will stay where it is. So will this one. This point is going to move across. You can count, or you can use this axis and this axis. They're going to reflect on each other. This one will be 1, 2, 3. So 1, 2. This point will move over here, and we have the center reflecting over to here. So now we can draw this circle. Like so. And so it says sketch the graphs of the relation and the inverse. We've done that. Determine how to use the equation of the relation to determine the equation of the inverse. Well, simply we switch the x and the y's. If we have x minus 3 all squared plus y squared equal to 9, the inverse becomes y minus 3 all squared plus x squared equals 9. Determine the equation of the inverse of the relation in this format. So really the x squared term should come first and the y squared term should come last. So really we're taking this equation and we're going to rearrange it so that we have x squared plus y minus 3 all squared equal to 9. So we can see the center now would be 0, 3 with radius 3. 0, 3, here's the center, radius 3. Write the equation of the inverse in D by solving for y. Solve this for y and verify the sketch in B on a graphing calculator. Okay, so let's solve this for y. So we have x squared plus y minus 3 squared equal to 9. If we're going to write it in this form, it's basically in that format already, except this 9 should actually be 3 squared. Sorry, we should have that actually. That's the answer that goes up here. For E, write the equation of the inverse of D by solving for y. So we're now going to take this and solve it for y. So what does that look like? If we solve it for y, we've got to bring the x squared to the other side. So y minus 3 all squared will equal, it's going to be negative x squared once it gets to the other side, plus 3 squared, or we can write it as 9, I guess. Solving for y, it looks like we're going to have to square root both sides. Now when we square root a variable, we end up with plus or minus our answer. If it's a cube root or a fifth root, we don't need to bother with that, the plus and minus. But when it's a square or a fourth root, we do. Simply because we know that the cube root of a value such as negative 8 has an answer of negative 2. And there's no other value. However, we know the square root of a number in here, if the answer is positive 2, we know that the variable could be 4 or negative 4. So when it's an even root, we have to put plus and minus. Okay, so the last part is to bring the 3 over. So I'm just going to write the equation over here. Y will equal, bringing the negative 3 over, it becomes positive. So 3 plus or minus the square root of negative x squared plus 9. State the domain and range of the relation and the inverse. So the domain of the original function was a circle centered at 3, 0. And if you remember what it looked like on the graph before I cleared it, this was the center here. So the domain went from 0 all the way to 6, 0, and 6. So it has to be greater or equal to 0, less than or equal to 6. The range went up as high as 3 and down below negative 3. So we can write negative 3 and 3 on either side with the y in the middle. And again, less than or equal to negative 3 is less than or equal to y. Y is less than or equal to 3. What about the inverse function? We know that was centered here. So the domain went from negative 3 to 3. In fact, it's the opposite of this, and the range went from 0 to 6. So we simply write domain and the x value ranged from negative 3 all the way to 3. And for the range, the y value went from 0 to 6. Using function notation to write an inverse. If a function f of x has an inverse, it can be written in this notation. It's read as f inverse of x. The inverse of f of x is if it's not a function, for example a parabola, when we reflect it in this line here, we get this. This is not a function. We can't use this notation. Okay, we have to write it like this instead. We're just swapping the x and y. Instead of y equaling f of x, x equals f of y. It's basically a bit of semantics, but since it's not a function, we can't use function notation like this. So the steps listed below, as far as writing the inverse, we take our original equation, whatever it might be, we replace f of x by y, we interchange x and y, we solve for y, and then y can be replaced by f inverse of x. So I'll just scroll down. Alright, note here the inverse of the function y equals f of x has this notation, and it's equivalent to this. But we'll use this when the function is not, when the answer or the inverse is not a function, it's just a relation. And don't get confused, as it mentions here, with the reciprocal. This is not a reciprocal function, it's the inverse. So we know the reciprocal of 10 is 1 over 10. If y equals 2x, the reciprocal is 1 over 2x, but this is not the inverse. Okay, class example 2, determine the inverse function, or the f of inverse of x, for the following. Remember the steps that are noted in the boxes above. We replace f of x with y, and we write the function like this. Now we can switch the x and the y's. And finally, solving for y, that means 2y will equal x plus 3 if you bring in the 3 to the other side. Now we have to divide by 2, so that y will equal x plus 3 over 2. Another way to write that is simply y equals a half x plus 3 over 2. For this one, again, y equals x cubed plus 4, and we will now switch the x and the y's and solve for y. So we'll leave the y cubed there, but we'll take the 4 over, so x minus 4. We're going to have the cube root, so we'll get y equals the cube root. Now if we're cubing, we don't have to bother about plus and negative, and we get the following, and that's the answer for that. And I'll just pause and scroll down. Alright, in class example 3, consider this function. Graph the function on the grid provided and state the domain and range. Now we know this is a parabola. We know that it comes down as low as negative 4. It will be centered on the y-axis. Remember this from Math 11. So these boxes are worth 2. So it's a scale of 2, 4, 6, 8, 10. Now remember how we used that ladder technique in grade 11. We moved over 1 and up 1 to sketch the next point, as long as the coefficient in front of the x squared was 1. We move over 1 and up 3. We move over 1 and up 5. We move over 1 and up 7. So that's up here. And remember, this is symmetrical, so we have points on either side of the y-axis. And now we can sketch this quite easily if you're a good artist, unlike me. So we get a parabola like that. Okay, state the domain and range. Well, we don't know the domain. In this case, is all real numbers, and the range has to be greater or equal to, goes down as low as negative 4. Here we're asked to determine x equals f of y. In other words, the reciprocal, the inverse, and solve for y. So they're asking us to use the equation. So let's write it as y equals x squared minus 4 from up here. And we'll swap the x and y, and then solve for y. So leaving y squared there, we'll bring the 4 over to the other side. Becomes positive. Square rooting, we have to use the square root, and we have to use plus and minus square root of x plus 4. Okay, now it says to graph this on the grid provided and state the domain and range. Well, if you use this y equals x line, this will map over, I'll just change the color, this will map over to here. We had a point here that would map over to here. We have a point here that would map over to here. And these points here, notice they're 2 out from the y-axis, so at a height of 12. So we'll get points here and here, and I can just sketch that. And you've seen in the past, this is really what we typically get when we take the inverse of a parabola. So we've graphed that. Now we've got to state the domain and range. So the domain now of the inverse function looks like it goes as low as -4. So x is greater or equal to -4. The range is going to be all real numbers. So member of the set of all real numbers. So notice the domains here and here have been switched. At the bottom here it says, is the inverse of f a function? Well, we know the answer is no. How could the domain or range of f, the original function, original parabola, be restricted so that the inverse is also a function? Well, what that's getting at is, really, if we want the inverse to be a function, half of this has to disappear. So in that case, half of the original function has to disappear, either the right or the left, just so that it will give us either the top or the bottom of the inverse. If I do away with, say, the left side of this equation, or this graph, all I'm keeping is all the positive x values, all the x values to the right of the y-axis. So in other words, all the positive x's. I could get rid of the other half and keep the left side, in which case I'm keeping all the negative x values. So you could restrict the domain either one way or the other by keeping all the x values on the right, so x would have to be greater or equal to 0, or, well, in that case, if you do that, you will get rid of this. So what does that mean? You're actually getting rid of the bottom part. Bottom part would disappear. If you restricted it where x was less than or equal to 0, you'd be getting rid of this part here on the right, so you'd be doing away with the top half. So that's what's meant by restricting. An example here, example 4, it's saying that Don determined the inverse of the function defined by this. He determined the inverse. He determined it to be this equation here. Now notice that equation is the equation of a parabola. This we know does not look like a parabola. He graphed the inverse of the function and obtained a parabola. Fair enough. Explain why Don's equation of the inverse is not complete, and why the graph of the correct inverse is not a parabola. What does this look like? Well, it starts on the x-axis at +3 and will go in this direction. Okay, so what does the inverse of that look like? Reflecting over, this will be here, this point here goes over here, and it will take off in this direction here. So this is y equals the square root of x minus 3. This is x equals square root of y minus 3. So explain why Don's equation of the inverse is not complete. Well, really, he's got this parabola that looks like this. Okay, and for some reason he's forgotten that when he's worked out the inverse, you will not get this part of the parabola. We can try and work that out, actually, if we actually take his equation and see what he did wrong. First of all, you switch the x and the y's. See if I make the same mistake. Now we have to solve for y. So we square both sides, and we'll get x squared equals y minus 3, and you can see what's happening. I'll bring the 3 over and I'll get exactly the same as this. So what's going on here? It's similar to what I discussed in class, and that's the fact that we're missing the plus and minus. When we get this, really, we do not get the other half of this equation, or this graph. So how do we show that in the equation form? That's the good question. So this is the positive square root. And when I switch the x and y's and square, I'm forming a variable with a square. Now I didn't have a variable with a square here, but when I square, I end up with a variable with a square. And we know when we solve or graph variables with squares, then or try and square root this again. When I think about it, if I square root both sides now, what do I get? I get x. And remember, when I square root a variable, I have to get plus or negative y minus 3. Now that was not the case here. Compare that to that. I have positive, but I don't have the negative. So that's what's going on here. So note, when determining the inverse of a function, the main restrictions, if any, must be included. We would have to, just like the example above, in example 2, we'd have to include restrictions if we want to restrict the inverse. So if we have a function like this, and we get a inverse function, an inverse relation, if we want this to be a function, we've got to get rid of half of that. So we've got to get rid of half of this by stating what restriction that would be. If the vertex lies right on the y-axis, we can just keep all the positive x values. If this vertex, let's say, lies at, well, let's say negative 3 and 0, then we have to say we'll keep all the x values from negative 3 upwards. We'd have to state a restriction something like x has got to be greater or equal to negative 3, and therefore we'd keep all these values here. Okay, last part before the assignment, and I'll tell you which examples to do. Basically, we are determining f of f inverse of x, and they also want us to calculate f inverse of f of x, and they're using this as the function. It's the same as class example 2a, and it's asking what do you notice when you calculate these. So if we write these out, let's actually just figure out what f inverse of x is. So we have to switch the x and the y's, and if you do that yourselves, you'll find that, well, we already did this in one of the examples above, in class example 2a. It was a half x plus 3 over 2. So now we'll use these two functions and figure out what this is and what this is. So let's do the first one. And what does that actually mean? It means f of f inverse of x. So we want f of, what is this? We can put this equation in here right now. It's a half x plus 3 over 2. And now we'll use this value in our f function. So this value goes in here and in here. Okay, so we will now take this and plug it in here, so we get 2 times all of this. And don't forget the negative 3. So multiplying the brackets out, we get x plus 3 minus 3 equals to x. So we can do the same for the other one, where we have f inverse of f of x. So what is that written in? Writing it like this. makes it easier to understand. We first of all take our f of x and plug it in here. That's 2x minus 3. And now we use this value in here and in here in the inverse function. So inverse function is a half of, our x value now is 2x minus 3 going in here. And that's the x, but don't forget the 3 over 2. So plus 3 over 2. We're going to simplify this. That becomes x and negative 3 over 2. And this is still here, positive 3 over 2. That also equals x. So they both equal x. So basically, we're saying that these two functions, composite functions, are equal to each other. So that is equal to this. Okay? And so whenever you have a situation like that, whatever this variable is, a or b or whatever, it always equals that variable. Okay, let me just pause and I'll think about which questions I'd like you to attempt in class. Okay, so the questions I'd like you to do in class are questions 1, 2, 5 odd, question 6, 7 odd, 8 odd, question 9, question 10a, question 10b, but for b just do parts 1 and 3, and then questions 11 through to 14. Alright, we'll see you in class.